We have now a tool to evaluate reflectance and transmittance of thin films on semi-infinite substrates. Sometimes we need to include very thick layers into our models. In practice, an example of a very thick layer is our substrate. It has a finite thickness which is significantly thicker than the thin film. Let's inspect the spectrum of thin and thick films and observe why the thick films are problematic in our coherent T-matrix model. Here is an example in MATLAB of a single film calculated with the T-matrix method. The thickness can be tuned. The refractive indices in the model are the incident refractive index is 1, the index of the film is 2, and the semi-infinite substrate is 1.5. From these refractive indices, we can calculate the corresponding reflection and transmission coefficients. The wavelength range in the simulation is 300 to 1000 nanometers. The transmittance is calculated from the T-matrix model by taking into account the refractive indices in the substrate and the incident index. When we change the thickness of the film, the resulting spectrum is shown on the right-hand side, and the thin film in general has a slowly varying transmittance spectrum. When the thickness is increasing, the periodicity of the oscillation will decrease. Eventually, the oscillation will be so dense that we cannot really measure it, but the measurement is an average over the optical bandwidth of the detector. So how can this be taken into account in simulations? T-matrix formalism is based on coherent waves. When the layer is thicker than the coherence length of the source, or bandwidth of the measurement instrument is larger than the oscillation period, we can formulate a matrix by using optical power. By looking at the first interface, the incident power is A1 and B1 is the reflective power. On the other side, A2 is the forward power and B2 is the backward power. We can relate these by reflectance and transmittance of the interface as A2 is the sum of reflectance from B2 and transmittance from A1. On the other hand, B1 is a sum of reflectance from A1 and transmittance from B2. Now we can solve these in matrix form for the powers as the incoherent propagation matrix takes only loss of the substrate into account and is where alpha is the attenuation coefficient of power. In case of two interfaces and lossy material in between, we have the matrices T12, propagation matrix, the interface matrix 2, 3. The transmittance and reflectance R1 and R2 are either simple interfaces or the reflectance can be calculated with the coherent thin film model. And in this case, the average transmittance through the composite of a thin film and a substrate is given by this expression, and the average reflectance is given by this expression.